we come to this point. अभी आप कंफर्म करें कि आपको नजर आ रहा है ये स्क्रीन, ये पीडीएफ फाइल जो मैंने खोली अभी। आ रही है नजर?
जी सर, जी सर नजर आ रहा है।
अच्छा। So I will not go through this because you already ये माइक बंद कर दे जिसका भी ऑन है। तो ये शुरू वाली डेफिनेशन मैं रिपीट नहीं कर रहा हूँ, ये हमने काफी दफा किया है। XI, Bernoulli, SM, SR, they are also they are binomial, and then we want to have another random variable which is conditioned on something else. And the idea was that this same problem can also be viewed as if you have a box of m objects. So if you see this omega 1 up to omega m, these are m objects. Normally you have to be very careful here. Normally in problems you hear something like, for example, 4 red balls, yeah, and 3 white balls. For example, if you hear something like that, so you have to distinguish between these red balls. So red 1, red 2, red 3 and 4. This is what we mean by these m objects, yeah? Because you have m objects, so even if they are not distinguishable, you have to make them distinguishable, because otherwise you do not know how many. यहाँ पे आप ये तो नहीं करेंगे ना कि R और Y W कर देंगे, इससे सेट जो बनेगा सिर्फ 2 एलिमेंट्स होंगे ना, so ये नहीं होगा. What we mean by red and white here is the subsets, yeah, the red subsets and the white subset. So because we are randomly picking, so each element has a probability 1 over m of being picked or selected, and then the probability of success. So A represents the success, A complement represents the failure, R over m is the success probability, m minus R over m is the failure probability. So if you focus only on one trial, the first one, that is a Bernoulli trial, because Bernoulli trial only requires you to have 2 possible outcomes, yeah? Bernoulli experiment, I would not call it Bernoulli trial, I would call it Bernoulli experiment, because trial is a word used when you are repeating it and it stays independent and identical. So we can only discuss the first experiment, so it's better to call it Bernoulli experiment. So now if I start with draw 1, so instead of experiment 1, I will simply say draw 1. For draw 1, we have that Bernoulli random variable ki, yeah, success indicator of draw I, and k1 is equal to 0 is failure, k1 is equal to 1 is success. So these are the 2 probabilities. I think by now you should be very comfortable with this. What is new is the dependency of draw 2 on draw 1, yeah? So here I am listing, in this row, in the top row, I am listing values of k1. There are possible values of this k1. Here I am listing possible values of k2, and 0, 1, 0, 2. It's just like truth table, yeah. And here I want to have a table for the conditional probability of the second draw on the first draw. Yeah, k2 is the success on the second draw. K1 is the success on the first draw. So you should, I think it should be very easy for you to understand this entry. What this entry means is that if you have a success on the first draw, the success on the second draw, the probability will change, because one success has the number of elements responsible for success that has decreased, and the total number of elements has decreased anyway. So in all these probabilities, the denominator will always be m minus 1, because one element is reduced anyway, and nothing happens to this probability because that was success, and so on. So we dealt with this last time as well. Now what if you multiply these 2 probabilities? Yeah, for example, if I want to know the probability of k1 taking this value intersection k2 taking this value, sorry, yeah, so this will just be the probability of k1 equals k1, and this probability I know, yeah, from there. and then I just multiply this with this conditional probability, which means that I'm just using these two, this unconditional probability, I multiply element by element with this table, and then I should get a table of joint probabilities. This is my joint distribution, that K1 takes this value, K2 takes that value, and just a simple product. Yeah. And remember this subscript 2, it should be easy for you. For example, m minus r subscript 2 is the number of permutations, so it will start with m minus r, and you will have a following factorial, and in total you can only have two elements, two factors. So the next will be m minus r minus 1, because you only have two factors, and same goes for the others. Now instead of having these tables, it's better to look at this as a tree diagram. So if I start from here, the first experiment, or the first the first draw, I would say, the first draw will either be a failure or a success with these two probabilities. You can verify this. And from this point onward, if you look for a second failure, you had a first failure, so the number of elements as well as the number of failures decrease, so minus 1, this doesn't decrease, and so on. And if you start with this one, if this is a success, another success means that both the number of successes, possible successes decreases, and so on. What you need to note here is that you can spot a pattern here. When you go from, because here in this path successes did not change, so this number, the numerator r goes there unchanged. Now the denominator will change anyway, m minus 1, m minus 1. Here it will be m minus 2, m minus 2, that will not change. And similarly here, this entry comes from that entry. So this is something which you can remember. Yeah? Whatever has not changed will not change in the next trial. In the next, draw. I'm using the word trial again and again. This is draw 1. So this line is draw 1. This line is now draw 2, and so on. And the last one will be draw 3. So the same pattern happens there as well. Okay. This number, the numerator comes here as a cross. Yeah. And this numerator, wait a minute. Okay. So that pattern is actually, you can see that here as well. Yeah. This r minus 1 goes there as r minus 1. And so on. So I would encourage you to actually have a look at this table, just zoom it, and everything I have written here, it makes perfect sense. Yeah, it's just because you have without replacement, yeah, and ordered, so this makes perfect sense. So if I now move on, and I can use the law of total probability combined with conditional probability to calculate probabilities of any of these. For example, what does this 0, 0 means? That K1 is 0 and K2 is 0. This 0, 1 means K1 is 0, K2 is 1. And this is a joint probability condition in the intersection. This is then another intersection. So you just go recursively and you can work out all these probabilities. Yeah. So if I ask you a question, let's say from that table I have this probability, the joint probability. K1 is K1, K2 is K2. Let's say I know this. So if I know this is kind of a joint distribution. How will I use this to get this probability? Remember, this is conditional probability, this is unconditional, and that is the joint. I will use the law of total probability. Yeah, that's why we call it the marginal distributions. So I will just sum this, yeah, over all possible values of K2. Yeah, if I sum this, this is the law of total probabilities says exactly that, because K1, sorry, this is wrong. This is if you sum this over values of K1, not over values of K2. So you have two variables, and if you sum it, if you sum their joint probability with respect to some variable, that variable will disappear and you will only be left with the other variable. And if you follow that procedure, you can see that the unconditional probabilities for K2 are exactly the same. You had this R over M for K1 as well. Now you have for K2 as well. This M minus R over M was the value for probability of K1 equals 0. Now you have the same for K2 is equal to 0. So it has not changed. Now that doesn't mean that it has no memory. It still has memory. But the memory is captured by the conditional probabilities, not by the unconditional probabilities. And now if we work this out further and say I now want to know how is draw 3 conditioned on draw 2 and draw 1, because draw 3 will depend on draw 2 as well as on draw 1. You can see it there. Yeah? When I say draw 3 depends on both these numbers. So this is the result of draw 1 as well as draw 2. So if I work that out, and if I fill this table for the conditional probability of K3 taking a value, and you condition it on the two values in the first draw and in the second draw, first draw, second draw. So I'll just write 1 for first draw, 2 for second draw, and I want to condition a probability, yeah, of some event in draw 3, and the conditioning is done on the two draws. If you have this table, this looks very familiar to your truth table, and you have all these probabilities. So this should also make sense, yeah. For example, if I want to understand the first one, how will you understand the first one? Remember, K1 is 0, so the first one was a failure. K2 is 0, the second one was also a failure, and now you are also asking for a failure. K3 is failure. Yeah. So minus 2 means that two failures must be subtracted. That's how it depends. Yeah? And here, if you look at this one, the first was a failure, the second was a success, and what you are asking for is the failure. Yeah, so only one failure has occurred before, so minus 1. Yeah? This success will change some other probability, not this one. So all these probabilities make perfect sense. I mean, they all are derived from one rule, and that is without replacement. If you know the meaning of without replacement, you should be able to fill this table. And similarly, I can use the law of total probability again and conditional probability to now work out the joint probability of the three events. Yeah, K1 taking one value. So this is now a distribution for all the three draws. Yeah, draws 1 up to 3. And here is the table. Now this table will not be so revealing, but what you can do is that if you think of this as one event, if you think of this as another event, and if you think of this as another event, and let's say it's like this intersection there, and if you now divide this by one of the probabilities of one of these, let's say if I divide this by the probability of the second event, yeah, so what will happen? Yeah, if you remember the probability of something given something, that conditioning event is in the denominator, and in the numerator you have the joint. So here I have the joint probabilities. The probability of intersection, I divide by sum, so that will be the conditioning, and it will be the probability of basically no, I think I'm not doing that at this point. Sorry, I think I skipped one step. You can't do this here. You can only go from, so this is not what we are doing here. What we are doing here is that, let's say I have probability of one event, intersection second event, intersection third event, and if I sum this over the values related to the first event, yeah, so this has probabilities related to K3, K2 and K1. You are summing it, you are summing it over all possible values of K1. Now that K1 will not be relevant in the answer. The answer will only depend on the, sorry, this is also a typing mistake. This should be K3, yeah. No. I need one table for K3 is equal to 1 and one table for K3 is equal to no, this K3, yeah, this K3 comes here actually. The possible values of K3 are there, so you should not write 1 or 0 there. That was a typing mistake. Yeah. Remember, if you look at the first table, you will see what I am talking about. In this first table, whether you look at the conditional probabilities or at the joint probabilities, remember one of these is in the rows and the other is in the columns. Yeah, whether you are looking at the conditional probabilities or at the joint probabilities, we must see the same pattern there. Yeah, this K2, one of them is in the rows, K2, the other must be in the column. Yeah. And because that table has 3 variables, K1, K2, K3, and you are summing over K1, that will disappear and you will be left with a table which is only for K2 and K3. You got it? Now you must be asking why we have K3 is equal to 0 and K3 is equal to 1. This is because in two-dimensional table I must do something. Yeah, if I leave this open, I do not have a third dimension, so I cannot come out of the page for K3. For example, I'm using this one dimension for the values of K1. I'm using the other dimension for the values of K2. So if you are okay with geometry and linear algebra, I need a third dimension for the values of K3. Now because I'm using a page, which is a two-dimensional surface, I have to separate the two values in a different way. Yeah, just like you use truth table of 3 variables. Yeah, you have 0, 0, 0, 1, 1, 1, 1, 0. We can't do this here because we have probabilities. Yeah. So anyway, you can then move on from this joint probability, because this is joint probability. Yeah, K3 and K2 are involved, and joint means intersection. So if you divide this by, let's say, one of them, let's say if you divide this by the probability of K2, taking some value, you can turn this into a conditional probability. Now you can do all these things at home because this is very laborious thing. What you must focus here, because this is here I need to help you make sense of all this. If you look at this table, this is the dependency of the third row on the second row. This matches exactly with the table we had for, instead of going upward, I'll just write the formula. The table we had for the probabilities related to the second row, conditional on the probabilities, sorry, on the events related to the first draw. Yeah, so draw 2 depending on draw 1, that table was exactly the same as this table. So the dependency of draw 2 on draw 1 has the same probabilities as the dependencies of draw 3 on draw 2. Yeah? Just read this out. The dependency of draw 3 on draw 2 matches exactly the dependency of draw 2 on draw 1. If you follow the similar procedure for other combinations, you will also learn, and you can do that yourself, that the dependency of draw 3 on draw 1 is also the same as the dependency of draw 2 on draw 1. Every time you will get the same table. This is amazing, yeah? So even though you do not have independent events, they are still dependent, but because of this special relationship, some magic happens that the dependency of draw 2 on draw 1 has the same form as the dependency of draw 3 on draw 2. Similarly, the unconditional probabilities of draw 1 or related to draw 1 are exactly the same as the unconditional probabilities related to draw 2, and they are also exactly the same as the unconditional probabilities related to draw 3. So if I now somehow work this out, the unconditional probabilities of draw 3, this will again give me the same formula. For K3 is equal to 0, I will again get M minus R over M. And for K3 is equal to 1, I will again get R over M. So neither the unconditional probabilities change nor the conditional probabilities change as long as you stick to just two of them. And two of them doesn't mean that they have to be consecutive. So the dependency of draw 3 on draw 1 is also the same as the dependency of draw 2 on draw 1. So you just take any two draws. Maybe you take draw 5th and draw 9th. They will have the same dependency. Similarly, the unconditional probability. So if I now wrap all this up, this is my conclusion. The conclusion is this. I'll get to this name in a while, but the conclusion is that all the R draws, remember, sorry, this is not R draws, this is N draws. Yeah. Let me go back to that setting. I have M objects. One subset has R elements, the favorable ones. The other subset has M minus R elements, and I draw N objects. Yeah. I have N draws. So all these N draws, it's actually because of that old notation that I forgot to fix this. In all these draws, so I can take, so here I got it right. Ith draw means that I can take any value from 1 to N. For each one of them, the unconditional probabilities of any Ki taking 0 will always be M minus R over M. Any Ki taking 1 will always be R over M. This is very interesting, yeah? That even though you have without replacement, the unconditional probabilities don't change. And the joint distribution, the intersection of, let's say, probabilities related to the ith draw, this is draw I, yeah? Draw I, and draw J. Now I could be 1, J could be 5, I could be 2, J could be 9, anything, any two draws. The joint probability, which means intersection, will also be of the same form. Now interestingly, why we call it exchangeable RVs? Because this table was also for 1 and 2, yeah, and these formulas are also for 1. So you can replace all the variables as if they were related to the first one, and similarly you can replace all the pairs as if you were looking at the first pair. So the first pair, draw 1 and draw 2, this pair of draws is representative of all pairs of draws. That's the meaning of exchangeable random variables. You have a collection of random variables, K1, K2 up to Kn. They are all dependent random variables, but all of them unconditionally behave like K1 if you look at one variable at a time, And if you look at pairs of variables, any pair of variables, ki, kj, so k2, k3, k2, k9, any pair behaves as if they were k1 and k2. This will simplify our life. And I want to stop here because if there is any question, I would like you to ask. Because whatever we do after this will depend on this slide. So if you have any question on this slide, you can ask now. Any question? Huh?
asking for two.
No, you
आप
have to
ड्रॉ
be to get loud. मेरी आवाज सही नहीं आ रही.
तो मैं कह रही हूँ कि दो कंसेक्यूटिव फेलियर्स में आप ड्रॉ टू की वैल्यू कैसे लिखते हैं?
नहीं, दो कंसेक्यूटिव में ड्रॉ की क्या करें, समझ नहीं आई मुझे.
ड्रॉ टू की वैल्यू कैसे लिखते हैं?
नहीं, ड्रॉ टू की वैल्यू नहीं है. ड्रॉ टू पे दो वैल्यूज हैं. ड्रॉ टू पे वेरिएबल आपके k2 हो गया ना, तो k2 की दो वैल्यूज हैं 1 और 0. ठीक है, तो जो उसकी प्रोबेबिलिटी है k2 इज इक्वल टू 1 की और k2 इज इक्वल टू 2 की, वो प्रोबेबिलिटी वही है जो वेरिएबल k1 की लिए थी. समझ आ गई? Maybe you can look at this diagram to see some understanding of this. Let me just remove everything now. Say this line is draw 1, yeah? This one circle means draw 1. This line is draw 2. And this line is draw 3. So if you look at draw 2, why am I writing 0, 0? Because here I can only come to draw 2 when I have my draw 1, yeah? So 0 means first draw had a 0. This 0 means second draw had a 0. Yeah? Now this is 0, 0. And this is 0, 1. Can you tell me what if I add these two probabilities? I will have a probability of this 0, 0 and I will have a probability of 0, 1. If I add these two, what will I get? The probability of what? Can anyone tell me? Which of these two does not change in this addition? This 0, yeah? And that 0 is a value of what? That 0 is a value of?
Failure in the first row.
Yeah, k1 is equal to 0. So this was not so exciting, yeah? Because we already know that, yeah? So adding this will not be so exciting. Let's try to do something else. Let's try to add this probability, yeah, with this probability. What will I get out of that? Anyone?
K2 is equal to 0.
K2 is equal to 0 because you don't care about what happened in the first draw. That's what we mean by summing over values of K1. Yeah. So it's K2 is equal to 0. You add these two yourself and you will find out that it is exactly the probability you have for K1 is equal to 0. So it doesn't matter whether you ask this question there or here. Similarly, you do that there. You add this, for example, with this, yeah, and with this. So if I add all of them, this, because they all have one thing in common. The last one is a 0, yeah. the last one is a 0. So if I add all of them, I'll get the probability of K3 is equal to 0, and that will be the same as probability of K1 is equal to 0. Similarly, if I take the conditional probability between any two, whether it be between 2 and 3, when I say between draw 2 and draw 3, maybe this is confusing you. I don't mean to say that draw 2 is an event. No, draw 2 is an experiment. Draw 3 is an experiment. Any event of draw 2, any event of draw 3, if you condition any event of draw 3 on any event of draw 2, that conditioning will be the same as if you condition that type of event on draw 2 on that of event of draw 1. So if, for example, if I write it in my mathematical language, what I mean is this: probability that K1 takes any value. Let me just write K here, small k. Small k can be either 0 or 1, so that I don't have to write it again and again. I don't want to write an equation for 0 as well as 1. This will be the same as the probability that K2 takes that same value. So for example, if this is 0 and if this is 0, these probabilities will not change. That will also be equal to the probability that, and so on. This will be true for all the n draws. You got this point? And you can verify this yourself. Don't trust me. The second one, the dependencies. So let me write now the cool thing about this tree diagram for dependencies. The probability of K2 taking some value, let me just write any small value, K, small k2. K2 can be 0 or 1. Conditional on K1 taking some value, and you can choose this. This is the same as if you ask the same question. Actually, let me, instead of K2 and K1, I'll use some other language. Let me write, let's say A and B, so that I don't change it from question to question. So I do change the draws, so draw 1, draw 2, but I don't change the value. So if A is 0, it will remain 0. If A is 1, it will remain 1. So it is the same as if I ask this question for draw 3 and draw 2. So K3 equals A, K2 equals B. If I do the same for, let's say, between 1 and 3, so let's say K3 equals A given K1 equals B. I am asking 3 different probability questions. They are all conditional probabilities. This is an event of draw 1, This is an event of draw 2. And it's up to you. If you choose this A and B, you should not change, otherwise you are not fair with this, Now you change the random variables to K2 and K3. Now you change it to K1 and K2. They all will be the same. You see? And I can now add to this another one. You can verify this yourself. Let me add.
तो ये भी हमने
Sorry?
डिस्कवर, ये तो वही बात है ना कि जो अभी हमने पढ़ा है कि any two events.
बिल्कुल, ये मैं असल में समझा रहा हूँ कि एक स्टूडेंट ने पूछा था कि ड्रॉ ट्रू ड्रॉ 3 क्या मतलब है ना, मैं वो समझा रहा था सर. ठीक है. So now that is what we mean by exchangeable ROEs. That if you look at a variable one at a time, they all behave like K1. And if you look at any pair of variables, all pairs behave like K1 and K2. Just remember this, Just remember this. Now, how will this help me? This will help me in ways you can't imagine. Remember, I don't have distribution. What I have is only conditional probabilities. You need to understand that we have how many variables in total? K1, K2 up to K. How many? Kn. Now I only know dependencies between pairs, yeah, and unconditional probabilities. I don't know, for example, I don't know this probability. I can work this out, but that's too complicated for me. For example, K1 equals 0, K2 equals 1, K3 equals 1, and K4 equals 0. You see, I do not have any formula for these complicated questions. That will be the complete joint distribution. I don't have that. I only have unconditional probabilities and pairwise probabilities. How can I use this, for example, to find the mean? One more thing, mean of what? If I add all these probabilities, sorry, if I add all these random variables, these ones, what do I get? Can anyone remember? How is this related to the question we started in the beginning? If you remember, this is that same S R, yeah, with some condition. Because here you have dependent random variables, you are adding them. For example, K1 is the number of successes in the first draw, K2 is the number of successes in the second draw, Kn is the number of successes in the nth draw. So this will give me what? The number of successes in how many draws? N draws. Remember, this is not a binomial distribution. This is not a binomial random variable because these are dependent random variables. Do you see this point? Can you confirm this point, that this is not equal to binomial random variable? Because in binomial random variable you are adding Bernoulli random variables. They are all independent. These are also Bernoulli random variables, but they are dependent. Yeah. So which means that I know the expectation of each one of them, Ki. For each I, the expectation of Ki is R over M. Do you agree with this? Why should this be true? And can anyone explain that? Why should this be R over M for all Ki's?
Because in Bernoulli trial, our
Because they are all
expectation
Bernoulli
is
random variables, and we know that the probabilities are the same, unconditional probabilities, and the expectation of any Bernoulli random variable is equal to the probability of success. So that R over M doesn't change. Yeah. Now, similarly, I look for pair. I will solve this thing there. Yeah. Remember, let's say I have one Bernoulli random variable K1 and one Bernoulli random variable K2. I just do it for K1 and K2. So what is K1 times K2? Can anyone tell me? Let me give it a new name. Yeah. Let me call this X. What are the possible values? Help me write the possible values here. It will also be a, because it will be either 1 times 1, 1 times 0, 0 times 1, or 0 times 0. Yeah? Just like a truth table. So if I want to know the expected value of K1, K2, what should I do? Do you remember the expectation formula? This is G of K1, K2. Yeah. So what do? You write values of that G here. So you write small K1, small K2. Yeah. And you add over all possible values of K1 and K2, which is either 0 or 1. And then you multiply this with what? Anyone? Probability of what?
probability of Q1, Q2.
The joint probability, because this is a 2 variable. Yeah? So it means that K1 takes that value, yeah, and K2 takes that value. That's what I'm going to do. So now you have to help me all possibilities. Yeah. What is the first? I'm now writing that sum here. So what is the first possibility? That K1 is 0 and K2 is, let's say, anything. 0 times anything is 0, so if K1 is 0, this answer will be 0. Got it? I don't care what is the probability there. If K2 is 0, I will still get a 0. I will get a non-zero answer when both K1 and K2 are 1, yeah? Got it? So if K2 is 1 and if K1 is also 1, what is the value of this transformation? 1 times 1. So I just write 1 times 1. And then I multiply it with what? Probability. Tell me that K1 is 1 and K2 is 1. This will be the expectation of K1 times K2. Can anyone tell me what do I get out of this? This looks complicated, but it's very easy. This is just a joint probability between the first two draws, yeah? This is a joint probability of two events. One event is related to second draw and the other event is related to first draw. What do I do when I forget about this because this disappears. 1 times 1 is 1, so I don't care. This is the probability of what? I can start with K1 is equal to 1 and then I can use the conditional probability, which is K2 equals 1 given K1 equals 1. Can anyone remember what is this probability? This one?
R following factorial 2 and M following factorial.
R over M. This is R over M. This is just one trial, one experiment.
The other one is.
And this is just with the second on first. तो ये क्या था? R minus
1 and
M minus 1. क्योंकि ये number of possibilities भी कम हो गए हैं overall और number of successes भी कम हो गए हैं ना? समझ आ गई बात?
जी, तो सर ये पूरा वही है ना, R following factorial.
R following factorial बिल्कुल यही था. R following factorial 2 और M following factorial 2. इसका मतलब ये है, अब ये हमने किस पेयर के लिए किया है? ये हमने सिर्फ K1 और K2 के लिए किया है. अब अगर आपको मेरी बात समझ आ रही है जो पहले किया है, अगर मैं किसी भी Ki और Kj के लिए एक कैलकुलेशन करूं तो मुझे क्या आंसर मिलना चाहिए? यही मिलना चाहिए ना, वरना फायदा कोई नहीं है ना. So this answer should be the same as if I am doing this calculation for K1 K2. ठीक है. और इसी तरह जो पहला आंसर था EKI is the same as if I am doing that for EK1. So this is what I am actually doing. अच्छा, ये तो मैंने basically ये मैंने यहाँ पे एक और तरीके से किया है. हाँ, ये expectations R times R minus 1 M times M minus 1. हाँ, इसमें एक चीज है कि जो मैंने आपको आंसर बताया है, ये जो फॉर्मूला है ना, ये Ki Kj, ये तब होगा जब ये I और J डिफरेंट होंगी. When I and J will be different. For example, K1 K2, K1 K3, K2 K9, yeah, K5 K10. What if I and J are equal? फिर क्या होगा?
उसका वो एक ही वर्नोली.
हाँ, लेकिन ये रिजल्ट कैसे चेंज होगा? इसको मैं चेंज कर देता हूँ ना. इसको मैं रिप्लेस करता हूँ इस फॉर्मूले को. So I will have expectation of K1 times K1. Yeah. समझ आ गई? And if I can do that, this will be the same as expectation of K2 times K2, which is K2. So K2 squared, K3 squared, they all have to be equal to expectation of K1 squared because they are all similar to K1. Now what is the expectation of K1 times K1? It will only be non-zero when K1 is 1, yeah? Times the probability of K1. What is the probability of K1? is equal to 1, R over M. What? So I will get this answer when I and j are different. But if I and j are same, I will get this simple answer. You got my point? Why is this important? I want to write an expression for expectation of ki times kj. Now ki times kj doesn't mean that I and j will always be different. They will sometimes be different because I and j can take any value from 1 and n, 1 up to n. Now if you, let me show you something and you will know what I mean. If I have, let's say, a matrix of values, yeah, here I have values of a, here I have values of j, and I have possible matrix, yeah. So on this diagonal the values will be same, and outside the diagonal the values will be different. So for this diagonal, when I and j are the same, I will have a different formula. समझ आ गई बात? So let me now write this down. Expectation of this product will be, if I equals j, I will have a simple answer, R over M, because ki and kj are the same. If they are different, then I had this answer, that R following factorial and M. I have simply combined this into a compact notation. You see?
सर लेकिन इसमें ये R over M plus भी तो हो रहा है आपके फॉर्मूला.
क्या क्या?
R हो रहा है. R by M ऐड क्यों हो रहा है?
इसमें अभी बता दो आपको. ये समझ आई है? ये वाली बात समझ आई है? ये वाली बात
जी जी. When I is not equal to j, it becomes R over M plus R over
तो
M.
आप इसको ऐड करें, आपको आंसर वही मिलेगा.
अच्छा.
आप इसको करेगा ना, ये जो वर्सन ब्रैकेट है, ये 1 कब होगा? जब आपके पास ये सीन होगा ना.
जी.
और आप इसको वेरीफाई कर सकते हैं, m+1 उधर चला जाएगा, m कैंसिल हो जाएगा, and you will have r minus 1. Because this minus 1 will come there, it will become r minus 1. ठीक है?
Okay, right.
And when I is equal to j, this will be 0, and you will just have r over m. अब समझ आ रही है बात आपको?
जी जी.
अच्छा, अब इसका मुझे क्या फायदा है? इसका फायदा मुझे ये है कि if you remember the slides on covariance was defined as the covariation. Ki, how different is it from its own mean, and how is kj different from its own mean? You take the product and then you take the expectation value. You remember this? And if you multiply this ki with this kj, you will have ki times kj, उसका expectation. फिर ये ki इस kj के साथ मल्टीप्लाई करेगा, ये इसके साथ मल्टीप्लाई करेगा, वो कैंसिल हो जाएंगे, and you will have just expectation of expectation is the same. Yeah. So you have the expectation of the product minus the product of expectation. This is how you remember it. The covariance between any two random variables, if you follow this formula, is the product of expectation subtracted from the expectation of the product. आपको इसका भी पता है, आपको इन दोनों का भी पता है. Plug करें and you get this formula. So I have the covariance between any two random variables. And if ki and kj are the same, for example, if I and j are the same, this formula also gives me the variance. क्योंकि variance कब बनता है? जब I और j दोनों क्या होते हैं? So for example, covariance of k1 comma k1 will give me variance of k1. क्योंकि this will be k1 minus expectation of k1 minus square. जब square करते हैं, expectation लेते हैं, आपको क्या मिलता है? Variance. अब इन सब का मुझे फायदा क्या हो रहा है? मुझे पता है कि मैं जिस चीज में इंटरेस्टेड हूं, मैं इंटरेस्टेड हूं नंबर ऑफ सक्सेसेस में. नंबर ऑफ सक्सेसेस मेरे पास क्या है? सिग्मा ki, I from 1 to n. तो मुझे अगर इस नए रैंडम वेरिएबल का मीन चाहिए तो मैं क्या करूंगा, आई विल जस्ट ऐड ऑल दीज मीन्स, r over m will be added n times, so it's n times r over m. I have my mean for this new random variable without even knowing its complete distribution. You got this? And now I can also have a variance. अब वेरिएंस में ये इंडिपेंडेंट नहीं है, तो आप ये तो नहीं कर सकते कि वेरिएंस ऑफ द सम इज इक्वल टू सम ऑफ वेरिएंसेस, लेकिन आप फॉर्मूला तो लगा सकते हैं ना। वेरिएंस आपको पता है क्या होता है, लेट्स कॉल दिस फॉर सिंप्लिसिटी, लेट्स कॉल दिस x, या सो वेरिएंस के लिए मुझे क्या फॉर्मूला लगाना पड़ेगा, एक्सपेक्टेशन ऑफ x माइनस एक्सपेक्टेशन ऑफ, आपको याद है मैं ऐसे करूंगा ना, एक्सपेक्टेशन ऑफ x माइनस, और यहाँ पे भी एक्सपेक्टेशन ऑफ x होगा, और फिर मैं ये करूंगा, दिस इज व्हाट आई मीन बाय वेरिएंस ऑफ x। मैंने यहाँ पे सिर्फ ये वैल्यूज प्लग किए हैं, x की वैल्यू प्लग की है यहाँ पे, और ex मुझे ऊपर से मिल गया है ना, ये। अब मैं एक काम करता हूं, और फिर इसका स्क्वायर मुझे लेना पड़ेगा, ये यहाँ पे स्क्वायर लेना पड़ेगा, स्क्वायर के बाद ही आप इसको वेरिएंस कह सकेंगे। नाउ लेट मी डू सम ट्रिक हियर। This summation and this summation can be taken common, so I'm taking that summation common, और ये ना मैं स्क्वायर को छेड़ रहा हूँ ना मैं इस e को छेड़ रहा हूँ। Note this down, okay? I'm not changing this e and I'm not changing this squared. I'm just taking this summation out, yeah? So ki अपनी जगह पे रह जाएगा, और समेशन जब बाहर आ जाएगा तो एक्सपेक्टेशन ऑफ ki, एक्सपेक्टेशन ऑफ ki। समझ आ गई बात? अब मुझे क्या करना पड़ेगा, नाउ आई हैव ए सम ऑफ दीज डिफरेंसेस, और मैं उनका स्क्वायर ले रहा हूं। तो ऐसे ही आपके पास जिस तरह ये होता है कि a प्लस बी प्लस सी प्लस डी, और आप उनका क्या करते हैं, स्क्वायर करते हैं। तो आप क्या, इसमें आप क्या करते हैं, यू टेक स्क्वायर ऑफ एवरीथिंग, पहले सबका स्क्वायर ले लें, उसके बाद फिर क्या करते हैं आप, ट्वाइस
A and B.
जितने भी पॉसिबल प्रोडक्ट्स है ना,
जी सर,
ए बी सी डी, और उन सबको ऐड करते हैं, ठीक है, एंड सो ऑन। अब मुझे ये बताएं, और इसके अलावा थर्ड का कोई पावर नहीं है, तो मैं यहां पे भी यही करूंगा। इसमें अगर आप गौर करें, इसमें स्क्वायर्स भी आ रहे हैं, क्योंकि आई और जे जब इक्वल होंगे तो स्क्वायर ऑटोमेटिकली हो जाएंगे ना। देखो ना, ये a टाइम्स ए भी तो इस a टाइम्स b की तरह है ना, समझ आ रही है बात? So I am just taking all the possible products and then I am summation. This is a double summation. So if you look at this, the variance of a sum when you have dependent variables is simply the sum of their possible covariances. मुझे covariance का फार्मूला पता है, मैंने ऊपर लगा दिया है, मैंने ये लगा दूं, डबल समेशन लगाऊंगा। डबल समेशन मैं सिर्फ, ये आप आराम से घर कर लेंगे, मैं सिर्फ एक टिप बताता हूं आपसे। अगर मैं ये पूछ लूं कि मैं if I add let's say 1 from 1 to n, what will be your answer?
one.
I am adding 1, इस समेशन का कोई फायदा नहीं है,
N आ जाएगा।
it will be n, it will be n, yeah. What if I add this summation again? So this will be what?
2 and 2 into n and square.
क्योंकि आप वो प्रोसेस रिपीट कर रहे हैं ना। तो यहां पे बेसिकली ये डबल समेशन है। ये क्या है? डबल समेशन है। मतलब मैं आपको अगर ये, लेट्स से मैं इसको यहां से एक्सप्लेन कर लेता हूं। ये आपने ये किया है ना, ये जो आपने, लेट मी यूज अनदर आइडिया। यहां पे मैं अब ये कर लेता हूं कि x1 प्लस x2 स्क्वायर, ये आपको समझ आ जाएगी, बल्कि x3 में इसके साथ ऐड कर लेता हूं। लेट्स से आई एम डूइंग दिस, या इससे आप ड्रॉ कर लें नतीजा खुद ही। तो आपका फार्मूला तो ये होगा ना, आपका जो आसान फार्मूला है आपका क्या होगा,
x1 square plus x2 plus x3 2x1 x2 और 2x2 x3 और x1 x3।
अच्छा, ये मैं बताता हूँ, ये फार्मूला बहुत आपके लिए यूजफुल है, लेकिन ये मेरे लिए यूजफुल नहीं है इस टाइम पे जो मैं यहाँ करने जा रहा हूँ। मुझे एक काम करने दें, x1 स्क्वायर को मैं ऐसे लिख सकता हूँ, ठीक है।
यस सर।
मैं n में से हर एक टर्म, हर एक को ऐसे ऐसे लाऊं, और ये 2 को भी मैं इग्नोर करता हूँ। 2x1 x2 का मतलब ये है कि x1 x2 plus x2 x1, yeah? So I have a product of all the possible pairs, a product of, तो मुझे ये बताओ अगर मैं इसको ऐसे लिखूं कि xi xj, ठीक है, ये पॉसिबल प्रोडक्ट हो गया, and I add this over I from 1 to 3 and I add this over j from 1 to 3, I should get the same answer। इस पे आप सोच लें जरा, समझ आ रही है अब?
सर लेकिन ये 2 वाली टर्म्स किधर जाएंगी फिर?
तो ये x1 x2 और x2 x1 x1 x2 भी आएगा, x2 x1 भी आएगा ना, ऐड नहीं होंगे वो। सोच ले जरा इस पे, आप सारे पॉसिबिलिटीज देखेंगे ना। चलो मैं इसको 2 के लिए एक्सप्लेन, 2 के लिए तो समझ आ जाएगी ना, इसको 2 के लिए कर लेता हूं। आई एम जस्ट टेकिंग इट xi xj i इज इक्वल टू 1 to 2, ताकि मैं जल्दी इसको कर लूँ ना, और j इज इक्वल टू 1 to 2। बताएं कैसे आएगा? पहले j इज इक्वल टू 1 to 2 को ना छेड़े, पहले ये इंटरनल सम लगा, तो क्या आएगा अंदर?
1 1
x1 x1 स्क्वायर हो जाएगा,
x1 x2
और x1 x2, j को आपने नहीं छेड़ना पहले। अब j की बारी है। x1 स्क्वायर को तो आप ना छेड़े ना,
और x2 x1 x2 x2 ही होगा ना, x2 का
एक
स्क्वायर।
सेकंड, यहाँ पे एक गड़बड़ तो नहीं हुई?
सर ये x2 का स्क्वायर होगा शायद।
कौन सा, ये वाला?
जी
नहीं, मैंने क्या किया है, x1, ये x2 नहीं है। अच्छा,
J
ये
आपने
लास्ट मैंने
हटा
गलत किया है, ये
दिया ना।
xj है, क्योंकि j को तो मैंने अप्लाई नहीं किया अभी ना, मैं किस खुशी में कर रहा हूँ। ये क्या है?
जी
मैंने i लगा दिया ना, i में j कहाँ से आ गया? तो the inner sum will be x1 एक मिनट, ये भी x1 xj होगा, एक सेकंड, नहीं, ये दोनों मैंने गलत लिखे हैं। It will be x1 xj plus x2 xj,
दोनों में से
it will be x1 xj plus,
सर जे तो अप्लाई नहीं किया अभी आप कह रहे हैं।
हाँ तो मैं j लिख रहा हूँ ना, सेकंड को मैं चेंज नहीं कर रहा,
और
मैं
ये
सिर्फ
आई की जे है, ये जो आपने समेशन में लिखा है।
देखो ना, ये इंटरनल i है और बाहर j है, एक्सटर्नल j को मैं नहीं छेड़ रहा, और पहले मैं इंटरनल अप्लाई करना चाह रहा हूँ, तो इट विल बी x1 xj plus x2 xj, ये i मैंने अप्लाई कर दिया ना। अब समझ आइए?
यस सर।
अब मैंने इंटरनल सम मैंने कर दिया है, अब एक्सटर्नल की बारी है, तो एक्सटर्नल में क्या आएगा?
x1 का स्क्वायर,
फिर
x1 x2 और x2
नहीं
का
नहीं,
स्क्वायर।
पहले जब j is equal to 1 के लिए ये भी कर देना, तो इट विल बी x2 x1, फिर j is equal to 2 कर दे, x1 x2 x2 स्क्वायर, आपके पास वही आंसर आ गया। बेसिकली इसमें दोनों आ रही है ना, आप जो जब 2x1 x2 लिखते हैं तो व्हाट यू हैव इज एक्चुअली x1 x2 प्लस x2 x1, ये इसलिए 2 आ रहा है, ठीक है। और ये सीन x1 x1 में नहीं हो सकता, x1 x1 एक ही दफा आएगा, ये नहीं होगा कि x1 x1 प्लस x1 x1। यहाँ पे बेसिकली वही हो रहा है, अगर आप गौर करें, हमने यही किया है इधर। And what you need to remember is that this summation is applied to 1 twice, so this will be n squared as I said, और बाकी आप लगा दें, you will get the variance of a sum of dependent variables. नॉर्मली ये इम्पॉसिबल होता है अगर आपके पास कोई जनरल केस हो, लेकिन यहाँ आपके पास बेसिकली हो ये रहा है कि सारे पेयर्स, ऑल द पेयर्स आर बिहेविंग लाइक k1 and k2, ये उसकी वजह से सारा हो रहा है. अच्छा, और यू कैन इवन गिव अ मीनिंग. कैन एनीवन रिमेंबर द वेरिएंस ऑफ द बर्नौली रैंडम वेरिएबल? वो क्या था? इस पे ज्यादा दिमाग ना खाए ना, आप इंजीनियर्स हैं, आपसे मैं ये एक्सपेक्ट नहीं करता ये, बट आई वुड स्टिल लाइक यू टू फॉलो दिस. आई वांट यू टू मेक सेंस ऑफ दिस आंसर. व्हाट वाज द वेरिएंस ऑफ द बर्नौली रैंडम वेरिएबल? याद है आपको? नहीं, जनरल p था और 1 माइनस p था ना.
तब वहाँ पे ठीक.
और जब ये हमने इनको ऐड किया था बाइनोमियल की केस में, तो वेरिएंस इसको हमने ऐड किया था ना, तो n टाइम्स हो गया था वो. अच्छा, अब वहां पे p की जगह यहां पे क्या आ रहा है? यहां पे सक्सेस r ओवर m है, ठीक है. फेलियर क्या है? दिस इज योर फेलियर 1 माइनस r ओवर m, करेक्ट?
यस सर.
और अगर ये डिपेंडेंट ना होते तो यहां पे भी आप n लगाते. यस. अब इसमें फर्क नोट करें, क्या फर्क है, कौन सा फैक्टर इसमें फर्क है? देखो ना, ये n इधर आ गया, ये n पहले भी है, r ओवर m भी आ गया, 1 माइनस r ओवर m. सिर्फ ये करेक्शन है, m माइनस n ओवर n माइनस 1, ये आपके पास करेक्शन टर्म है जो विदाउट रिप्लेसमेंट की वजह से आ रहा है. दिस इज द विदाउट रिप्लेसमेंट करेक्शन. दिस इज हाउ यू रिमेंबर फार्मूलाज, ठीक है. You don't have to actually memorize things. You just spot the pattern and you only have to notice this thing. The rest is just as if it were a binomial distribution. So now we need to attack the full distribution. मतलब हमने दो काम कर लिए ना. अच्छा, और इसमें हमने मीन भी कर दिया, वेरिएंस भी कर दिया, पेयर वाइज भी कर लिया. I want to know this thing. I want to say कि k1 is equal to k1, बल्कि नहीं, मुझे वो नहीं चाहिए. मुझे ये जो समेशन है ना, मैं तो इसमें इंटरेस्टेड हूँ ना. बेसिकली मैं इंटरेस्टेड सिर्फ इस सम में हूँ. इसको अगर मैं x कह दूँ, बल्कि इसको मैं असल में, मैंने पहले, आपको याद होगा, इसको हमने नाम दिया था, it was a sum similar to SR and we had this n comma m as subscript. अगर आपको याद आ रहा हो कंडीशनिंग जो हमने की थी शुरू में. Let me just remind you, this summation of dependent variable can be seen as if you had, it can be seen as if you are adding the Bernoulli random variables from 1 to j, from 1 to n, with that special conditioning, and that special conditioning is Sm is equal to n. And to remind myself that this conditioning will be there, so it is simply SR m comma n. ये m और n ऊपर आ गए, और r भी कहीं ना कहीं पे आना चाहिए. नंबर ऑफ जो पॉसिबल सक्सेसेस r है, ठीक है. तो मुझे इस वेरिएबल में इंटरेस्ट है. इन अदर वर्ड्स, आई वांट दिस समेशन. आप इसको फॉर एग्जांपल, फॉर द मोमेंट आप इसको y कह सकते हैं. आई वांट द डिस्ट्रीब्यूशन ऑफ दिस समेशन. अब मुझे ये बताएं, ये जो समेशन है, आई नीड n सक्सेसेस. n सक्सेसेस, कोई सिनेरियो बता सकता है कि n सक्सेसेस? हम यहाँ पे एक सिनेरियो इमेजिन करते हैं कि लेट्स से n को मैं 5 कर लेता हूँ, एज्यूम. तो मुझे कोई सीक्वेंस बताओ जिसमें मुझे, और लेट्स से ये समेशन जो है, मैं चाहता हूँ कि समेशन 3 हो. तो कैन समवन गिव मी a sequence of values of these 5 experiments or 5 draws, basically 5 draws, जिसमें मुझे 3 मिल जाए? Can anyone suggest a sequence of 5 draws? हर एक में मुझे आपने उस वेरिएबल की वैल्यू बतानी है। K1 की क्या वैल्यू होगी, K2 की क्या होगी, K3 की क्या होगी, K4 की क्या होगी और K5 की क्या होगी। पॉसिबल वैल्यूज बताएं मुझे।
सर 3 1 होंगे ना, 3 सक्सेसेस
हाँ तो
होंगे।
कोई सीक्वेंस बताओ ना, कोई भी।
1 1 1 0 0।
दिस इज वन पॉसिबल, और ये हमेशा जहन में ये पहले आता है ना, हालांकि ये
जी।
1 1 1 कहीं पे भी हो सकता है। सो इन अदर वर्ड्स, मैं अगर इस सीक्वेंस को जनरलाइज करूं, कैन आई से दैट K1 अप टू K, फॉर एग्जांपल इस सम को मैं रिप्लेस करता हूं स्मॉल k से, किससे, और ये जनरल है, n जनरल है, तो यहाँ पे क्या होगा, K1 अप टू क्या होगा, ये K स्मॉल क्या हो जाएगा। So I'm assuming that all the first K trials, sorry, K draws gave me a success. तो ये भी 1 हो गया, ये सारे क्या हो गए, 1 हो गए। तो बाकी क्या है, K और
0
ये K प्लस 1 से लेके कहाँ तक,
से लेकर KJ तक,
K
5
n
तक।
K n तक,
जो
जनरली K n हो गया। ये सारे क्या हो जाएंगे,
फेलियर्स 0।
अब मुझे बताएं, मैंने इस पार्ट को, डू यू एग्री कि इसको मैं ऐसे लिख सकता हूँ। आप ये ब्रैकेट अपने तौर पे यहाँ पे, ये ब्रैकेट, कैन एनीवन टेल मी कि ये मुझे ब्रैकेट यहाँ पे मैंने K1 इज इक्वल टू 1 को ब्रैकेट में क्यों नहीं किया, ब्रैकेट की मुझे ज़रूरत क्यों नहीं है, मैं ब्रैकेट के बगैर भी ये लिख सकता हूँ, क्योंकि जो यूनियन है ये Ki पे तो अप्लाई नहीं होगा ना, कि यूनियन की इंटरसेक्शन के लिए क्या चाहिए, इवेंट चाहिए ना। इंटरसेक्शन किस पे अप्लाई होगा, इवेंट पे। Ki इवेंट नहीं है, इवेंट क्या है, Ki इज इक्वल टू 1। So I am just taking, this is K1 is equal to 1, K2 is equal to 1, all the way up to Kk is equal to 1. I'm just taking that intersection. This tells me the probability of a streak of K successes in the first K draws. ये समझ आ गई बात। इसकी प्रोबेबिलिटी क्या होगी, K1 से स्टार्ट करें और फिर बाकी सारे क्या है, कंडीशनल प्रोबेबिलिटीज है। K2 गिवन K1, K3 गिवन K1 एंड K2, K4 गिवन K3 K1 K2 एंड सो ऑन। ये सारा किसी भी आयत के लिए आपको 1 से i-1 तक सबको कंडीशनिंग करनी पड़ेगी। वो सारी कंडीशनिंग उस ड्रॉ ट्री डायग्राम से आप लगा दें, यू विल गेट दिस फार्मूला सो इजी। या आप इसके बगैर भी कर सकते हैं। फर्स्ट का क्या होगा, r ओवर m, r ओवर m होगा या नहीं। सेकंड का क्या होगा,
सर
r-1 ओवर m-1 एंड सो ऑन। अब यही मैं इसके लिए भी कर सकता हूँ, एक दूसरे पार्ट के लिए, इसके लिए कर सकता हूँ कि नहीं। So I am now asking for the probability of a streak of n-1 failures in the last n-1 draws. So सबको मैं जीरो करके इन सबका यूनियन इंटरसेक्शन ले रहा हूँ from K1 up to n, वही कंडीशनिंग। और ये आपको भी समझ आएगी कि पहला फेलियर क्या होगा, m-r ओवर, ये क्या है, ये जो मैंने लिखा है पहला, इसका पहला टर्म क्या होगा, ऊपर क्या होगा, m माइनस,
पहले के एम तो खत्म हो गए, सही, इसलिए
k की वैल्यू क्या हो जाएगी, when n is ये मुझे कितने वो चाहिए होंगे, it will start from m minus r over, it will start from m minus r over m minus, ये मैंने नीचे क्या लिखा है,
ये कौन सा फॉर्मूला है?
पहले के स्ट्रीक में m-1 m-2 अप टू m-k-1 हो गया ना।
इसका लास्ट टर्म, इसका लास्ट बताओ वो क्या होगा, आखिरी वाला
m-k+1
m minus k plus 1, और m minus k plus 1 से जो अगला होता है वो क्या होता है, m minus k होता है,
m-k।
ठीक है। तो इसलिए ये m minus k से ही स्टार्ट होगा, ठीक है। ये जो नीचे लिखा है ये तो नंबर ऑफ फैक्टर्स है ना, कि कितने आपने लेने हैं फैक्टर्स, आपको n minus k फैक्टर्स लेने हैं। अगला क्या होगा, m minus r minus 1, और यहाँ पे एंड सो ऑन। ये सारा आप कर लें। now because you need this and this, you have to multiply these two. इन दोनों का आपको क्या करना पड़ेगा? This will give me the probability of that particular sequence. I just multiply, इन दोनों का मैं इंटरसेक्शन ले लेता हूँ, इसका और इसका, इनको मल्टीप्लाई कर लेता हूँ, और यहाँ से मैंने नोट किया कि ये k के बाद वही कंटिन्यू कर रहा है. ये तो डिफरेंट है ना, ये इन दोनों को आप मिक्स नहीं कर सकते, तो अलग अलग रहेंगे, लेकिन ये वही एंड तक जा रहा है, तो ये सिंप्लीफाई हो जाएगा. दिस इज द प्रोबेबिलिटी ऑफ एनी सीक्वेंस यू गिव मी. आप वंस और जीरोस को जहां पे भी रखेंगे, एक सीक्वेंस बताएंगे, मुझे प्रोबेबिलिटी आएगी. अब मुझे बताओ इस तरह के कितने सीक्वेंसेस हैं? इस तरह के इतने सीक्वेंसेस हैं, बिकॉज दीज k successes can be placed in the n slots. Basically you have n slots, 1 up to n, और इनमें आपने कितने सक्सेसेस फिट करने हैं? तो उसका n k आता है, आपको पहले पता है, n choose k. So all you have to do is that for each one of those sequences you have the same probability of n को ऐड करेंगे उतने ही दफा. ये आखिरी बात समझ आ गई ये वाली? This last one,
जी.
क्योंकि I am just adding all these. I have n choose k such sequences. All those sequences have one thing in common. What is common? They all have n successes. Sorry, no, they all have k successes. When they all have k successes, they all must have the same probability. So I just multiply this thing that many times, simplify कर देता हूँ, and I get my PDF. This is my PDF basically. Of course, PDF which is only defined for k belonging to the support. Restricted PDF हो गया नहीं. This is what we mean by hypergeometric distribution. इसको कहते हैं hypergeometric. अच्छा, मैं अगर ये उस क्वेश्चन पे आ जाऊं कि बेसिकली तो ये था ना, this question was as if I had no conditioning, no constraint, without replacement, and then I put a constraint, and that constraint is m over m is equal to n. ये बात अगर आपको समझ आ रही है तो मुझे ये बताएं, I can also answer this question in this way. The probability that this thing takes a value k, I just put it there. Yeah? Can I start from this question? Now, do you agree with me that this must be equal to this conditional probability? Anyone disagrees with that? अगर ये कंडीशन ना होता तो मैं इसकी जगह SR लिख लेता ना. फिर SR की वैल्यू क्या है मैं पूछ लेता, और मैं वही कंडीशन लगा लेता हूं. तो मैं कौन सी बात यहाँ पे नया कर रहा हूं? नहीं कर रहा हूं. ठीक है, ये बात समझ आ रही है ये वाली? और इसके बाद मैं सिर्फ लगा लेता हूं बेस रूल. कौन सा रूल? बेस रूल में आपको पता है कि P of A given B can be written as P of A intersection B, P of B, और P of A intersection B को आप उल्टा लिख सकते हैं, P of B, P of A given B, P of B. सॉरी, P ये मैंने उल्टा किया है. नहीं, P of A P of A, P of B given A, and P of B. Yes, you can do that. That's exactly what I have done here. If you think of this as A, if you think of this as B, so this is P of B, sorry, this is P of A, this is B given A, this is P of B. बाइनोमियल का फॉर्मूला लगा लूं, एग्जैक्टली वही आंसर मुझे आता है जो ऊपर आता. 2 different routes, I got at the same results. So whether I use conditioning, so you condition one binomial, listen to this carefully, you condition one binomial distribution over another binomial distribution, क्योंकि ये भी तो binomial है ना, SR भी binomial है, SM भी binomial है. Conditioning one binomial over another binomial gives you hypergeometric. And you saw that that's same hypergeometric. Hypergeometric को हम इस तरह लिखेंगे, HG नीचे जो first parameter होगा it will be the number of experiments, the number of draws. R is the number of favorable elements, number of possible successes. M is the number of elements in a box. और ये आप खुद वेरीफाई कर लें कि y should support be of this form. ये इसलिए मैं लिख रहा हूँ कि यहाँ पे ये binomial में you would not like this to be larger than that, and k you would not like k to be larger than r, and so on. Yeah. यहाँ तक कोई क्वेश्चन है? Any question? असल में अगली क्लास मेरी शुरू हो रही है तो इसको कंक्लूड करते हैं. बट डू रीड दिस डॉक्यूमेंट, इट्स वेरी डिटेल्ड. लेक्चर के दौरान शायद आपको समझ इतना जल्द क्विकली ना आए, लेकिन ये मैंने स्टेप बाय स्टेप किया है, सो यू कैन फॉलो द रीजनिंग एंड यू कैन ऑलवेज एक्चुअली पोस्ट अ क्वेश्चन ऑन फेसबुक इफ यू डोंट अंडरस्टैंड. ठीक है, लेट्स होप दैट दिस इशू इज रिजॉल्व, क्योंकि ये बड़ा मसला हो जाएगा अगर ये हमें इस तरह का करना पड़े तो. ठीक है, अल्लाह हाफिज. सॉरी, क्या? क्योंकि अजीब सी आवाज आई है.